皆様こんにちは。ダッソーシステムズの中で建設都市地域開発業界というグループの中でグローバルのマーケティングの責任者をしております森脇と申します。よろしくお願いします。今日のセッションを始める前にですね、簡単に少しご挨拶だけ差し上げたいと思います。今回のですね、セミナーで以前に我々何回か講演をさせていただいておりますが、過去においてですね、設計の自動化テンプレートを作ってそれをどのように活用するかということですね。それからあと施工のですね効率化をするためにどのようなシミュレーションをしていくかということを中心にですね過去お話してきました。で今日はですね少し違った観点でお話を差し上げたいと思っておりまして、カナダのですね大手土木エンジニアリング会社のですね SNC ラバリンという会社がございます。こちらの中でですねいわゆるコモンデータエンバラメントということで、さまざまなデータを統合して全体を管理していくというものを実装したという事例がございます。もともとその SNC ラバリにいた社員がですね、ダスシステムズに転籍しておりますので、そのビンスと申しますが、彼からですね、詳細なところをご紹介したいと思います。次のですね、ステージとしまして、BIM がですね、我々 BLMビルディングライフサイクルマネジメントと呼んでおりますけども、ライフサイクル全体を管理していくという段階に進んでいくと思っています。その将来に向けたですね、参考になる話ではないかと思っておりますので、ぜひよろしくお願いします。では、これからですね、ビンスの講演に入っていきたいと思います。よろしくお願いします。
Hello everyone, Vince Gattoli here, Industry Process Consultant at Dassault Systems. Today's presentation will take a look at a value transformation journey that occurred at SNC-Lavalin infrastructure major project sector during my mandate as a digital solutions manager. I hope you enjoy this presentation. Before we discuss the value transformation, I'd like to discuss a bit of the history with SNC-Lavalin and CATIA V5. This journey really began back in 2003 with the hydropower group adopting CATIA V5 for their hydroelectric power projects. A digital mockup was built. It was in fact inspired by the PLM and manufacturing practices back then. This was proofed out on hydro projects and further groomed to achieve a level of assets that would feed project workflows and processes. It involved a multidiscipline coordinated model, which would enable design, engineering, and coordination on projects. The asset data contained within the digital twin was shared for 6D FEA analysis, such as seismic and deformation. As well, construction optimization was achieved for 4D, 5D simulations. Moving forward, having important asset data now available, SNC-Lavalin began the transition to a data-centric approach and adopted Dassault Systems Smart Team and eventually migrated to Innovia 2012X. Libraries and catalogs were now derived from Innovia Common Data Environment. Combined with automation, reusability of data was now possible to perform on other projects such as substation design and dam rehabilitation designs. In 2017, SNC-Lavalin infrastructure major projects began a value transformation journey and via a value assessment to better understand the current state of projects, processes, and also look at how they collaborated on their projects. Based on an internal assessment, they found out that the teams worked in silos. Processes were linear, segregated, and not really integrated together. Risks were individually managed. Multiple platforms existed. Old technology still existed and mostly 2D. Agreements on the projects required unilateral efforts, really no sharing. As a result, one of the key takeaways was to bring a level of collaboration, leverage technology such as single source of information. This would initiate a collaboration through digital continuity in order to innovate and transform the way SNC-Lavalin would deliver projects. During the assessment, some key challenges were outlined, really emphasized by BIM tendencies back then, and therefore BIM presented siloed practices across the projects. The lack of collaboration between stakeholders on a project was evident. Models exported and imported into disconnected systems. Data silos therefore caused errors, version control problems, and required rework. No really seamless flow of information of project lifecycle. No integrated system really to leverage that BIM data that was being created on the projects. So interoperability of data, standardization was non-existent. Therefore, RFIs persisted from the construction site, that's requests for information, change management issues, and other issues as well. If we take a look at the unstructured platform image on the right, you'll notice a slew of platforms causing these data silos, erroneous data. The question now was, how can we improve? How can we eliminate some of the platforms? And this became a challenging question internally at SNC-Lavalin because it was the way they worked. It was not to be touched. So how can we proceed to make it better? Some of the platforms were really not BIM compliant. Trying to interoperate with formats was very difficult, with spatial distances, format import issues, as well for document management. And this created duplicated data exported to file structures with really no version control. So, having assessed the current challenges, we needed to adopt a vision and a strategy for transformation to occur and innovation to deliver the project. BLM, Building Lifecycle Management, was adopted. It combined both BIM and the PLM practices as an inspiration. SNC-Lavalin needed to transition towards an integrated project collaboration. With a look at the people, the process, and the technology, it was also assessed. As a result, the integrated project delivery approach was adopted. This would enable to leverage the teams by facilitating teamwork, openness, and collaboration. It improved processes by leveraging them and the knowledge from past projects. Control the risks by managing them collectively and sharing the responsibilities. And to leverage new technologies, adopt a virtual twin, work with BIM, 2D, 3D, 4D, 6D, etc., and really create a digitalization across the projects. Therefore, BLM as a strategy within SNC Fingerprint, as you see at the bottom here, was to be an extensive collaborative approach to plan, build, design, operate, and maintain an asset using the virtual twin and its single set of interoperable and reusable data created. It allowed SNC-Lavalin to leverage their distinctive end-to-end capabilities by taking full advantage of what we call the BIM uses, existing conditions modeling, laser scanning, interdisciplinary 3D coordination, quantity takeoffs, 4D, 5D, etc. This was early on in the early stages of a project and by conveying the right information to stakeholders along its whole life cycle. So as in any value engagement, a value transformation roadmap was introduced, as you can see here, top right corner. One that would foster and extend collaboration by achieving different levels or phases of implementation. First, we wanted to use the technology and the digital processes presented by BLM and the 3D Experience platform to have a better design, reinvest from 2D to 3D. We wanted to use a single integrated digital platform to store, share, and reuse the same data, the same true information across the whole life cycle of a project, implement and configure as required within the common data environment, and this allowed us to improve productivity, reduce the rework, and iterations. Thirdly, through design automation, we wanted to build accessible benchmarks, reusable data from our previous digitized projects. This would allow us to go in more detail in a short period of time, therefore reducing the risk and the cost, optimizing the schedule, and giving us an edge on competition. And finally, as I said, we wanted to define collaboratively the early phases of a project, the BIM uses, and maintain focus areas that would have the biggest impact on our prices, reduce the design, and the construction costs on projects, such as construction optimization. The BLM City was born as an initiative of the BLM Task Force, as you can see here in the video. It was my team, the team selected to head the digital transformation. The BLM City Virtual Twin was a means to educate, learn, inspire stakeholders, and demonstrate progression in our developments. It was a means to develop new innovative designs, engineering, and construction methods really tailored for the railway industry via the 3D Experience platform. From automated bridge designs, station designs with interoperability, track alignment, elevated guideways, super elevated guideways, add-grade guideways, and add-grade super elevation, as well as construction simulations was developed. In turn, it prepared the BLM task force to support projects and the different groups within SNC-Lavalin. Now, the intent of the BLM City was to be first a conceptual approach, as I mentioned, for development, and eventually, as we progressed, it became a more detailed using automated generative design concept. I wish I can show you more here, but the time is constrained. With the transformation roadmap outlined, some of the key transformation objectives were set. Key business objectives such as single source of information. We wanted to achieve an extended collaboration approach for IPD, that data-driven and data-centric engineering. So it would create a central, integrated, connected project repository. By the common data environment offerings, one of the key enablers would be to create that SNC-Lavalin customized digital space, that ecosystem for projects knowledge. It would create a social and collaborative platform on projects. For design optimization and automation, well, it was beyond parametric associativity. It was to leverage those knowledge templates and gain information from those engineering rules. Smart digital modeling. Through virtual twin, it was to create that single integrated model defined by a product breakdown structure and designing in context. Now let's look at this in detail. So for intelligent generative automation, which we call digital engineering, it was beyond parametric design. It was really capturing the engineering know-how, embedding them in the knowledge templates. Components-based design to develop smart digital models, and this combined with a change level of detail from 200 to 400 if wanted, if required. As an example, the bridge elements top left video was designed not only with component-based design and knowledge templates, but as well referencing a track alignment that was coming to us from AutoCAD Civil 3D. Yes, in fact, through a LandXML converter that we developed with Dassault Systems, if any changes was to occur to the track alignment during design phases, and trust me, this would occur often during the design phases, we're able to automatically import the track alignment into CATIA V6 to accommodate an update and the new version of track. This was completely revolutionary and changed the way we work today. On the right and below videos were the OCS overhead catenary systems design completely in CATIA V6. Automation that enabled almost 250 different combinations of wiring schematics, okay, as well as for a 67-kilometer worth of OCS designs. What I like about this development is not only the fact that we disrupted the industry in creating all this in CATIA V6 and as well automated, but the fact that we were able to really capture engineering know-how through engineering rules. This therefore allowed a complete validation of the OCS designs in order to reuse on the different projects. In fact, the engineer was able to configure himself the OCS system via an Excel spreadsheet, as you can see at the bottom, that would instantiate the components automatically. This was amazing. Now, it was not only developments, of course, we were able to bring this to real projects. As an example of a concrete structure spanning concrete piers, as you can see top left corner, yeah, this was designed for construction managers and the technical guys directly on site to help visualize and validate the rebar work and as well the tension rods. This provided quantity takeoffs on the go, on the fly, and volume of concrete for pouring. Basically, complete geometry simplified in the 3D experience for construction. Now, the image below center is actually a picture I took yesterday night passing by one of the spans with piers already poured. The second item of transformation roadmap was implementing a common data environment to serve projects. Some examples that you'll see of different configurations was achieved for project controls. A means to standardize a project requirements so as to replicate from one project to another. It allowed us to almost save 75% of startup times. Document management, document lifecycle management, configurations, for instance, that renamed automatically, non-CAD documents to standardize SNC-Lavalin to the naming structure that we created. And of course, creating a lifecycle of versioning of all these components. You're seeing this right now on the top left corner. As well as engineering work packages were defined for different project phases. This would automatically associate with project management, engineering work packages to designers so that they can follow into the next design phases. What was achieved for the virtual twin? First, we were able to create a usable virtual twin, that's important, that contained the product breakdown structure derived from a project work breakdown structure. That's key, and not only for clash detection. Allow disciplines to foster their designs and design in context, what I call concurrent engineering. But most importantly was interoperability of the BIM design data, either converting formats by using IFC, Industry Foundation Class formats, from other BIM authoring platforms, such as Revit and Tekla. For example, with Revit, we're able to bring in the Revit geometry with the IFC data model sets. With Tekla as well, we're able to bring them in. So that was key to creating that BIM integrated model. With asset data available in the common data environment, we began looking at construction optimization, your 4D, your 5D via Delmia platform. The example on the right demonstrates a data structure that is broken down based on construction practices and schedules. Process planning and sequencing via Delmia allowed us to plan, for example, the concrete pours with the time factor available and the sequences as well. Another key implementation was for systems engineering. With the 3D Experience platform, we began to look at requirements, the functional, the logical, and the physical pertaining to systems control on railway designs. As an example, for requirements of cameras, we were able to design the schematics for logical for 10 kilometers worth of wiring and synchronization. This with the physical, very important here. One of the key advantages was for duct bank design, following a track alignment. This was made possible because of the power of CATIA to actually follow the terrain conditions and the track alignment at the same time. This allowed us to design the the cableways through the duct bank. Finally, interoperability via connectors and converters. We were able to work with Revit by converting the stations and adding them to the virtual twin via the IFC data model sets. As well, working with Civil 3D, as I said, via Land XML, we could integrate the track alignment and automatically update it. Once in the 3D experience, this allowed us to expand our work via Innovia, CATIA, Delmia, and finally, Simulia. With that, I thank you for attending my session. I hope it was beneficial and inspiring. Thank you, and be safe.